Hey, AP Chemsters, this is Mrs. Vanderwall bringing you another edition of the Blank Wall series. So today we're going to start about section 15.5, which is called the auto-ionization of water and pH. Hopefully you're more or less familiar with pH. You've heard about it, you've seen commercials about it. You even did that in your first year of chemistry, whenever that was. You may not have heard of this term auto-ionization, but if you look at it, break down, what does that mean? What does that prefix auto mean? Well, it means by itself. So water by itself can ionize is really what that term means. Let's kind of go back and kind of lay some ground rules real quick, that if there is something that you didn't catch, or if I'm going too fast, or if you need to catch up, remember you can always pause this and go back and listen to me again if you really want to. And when I ask you to pause and do the work yourself, because there is some math in this section, you might want to have a calculator handy, that you should really do that. You should really pause, do the math, and then when I come back with the answers, you are checking your work, not just copying down what I do. So make sure you get into that kind of a habit, and hopefully this will make more sense. So, okay, go back earlier. In a previous section, we said that water can act like a base when acting with a strong hydrochloric acid, and water can act like an acid when you're acting with even a weak base like ammonia. And there is a term that will describe something that can act like both an acid and a base, and from previously we said that was called amphoteric. And water is not the only amphoteric substance. We even saw where ammonia can be amphoteric. I think in the very last section we saw how ammonia can act like a base, and it has a hydrogen it can give up, and it could act like an acid as well. So let's take more of a closer look at what water can do. It can act like an acid and base. And what happens if I just have a cup of water and all those millions and millions and millions of water molecules are zooming around at a certain speed, say at room temperature, and eventually some of them are going to have enough activation energy and the correct orientation, and if these two water molecules collide, something can happen. Well, what is that something that can happen? Right here, check this out. If these two water molecules collide with a sufficient energy and the correct orientation, look what happens to this hydrogen-oxygen bond. You can break this bond right here, and that hydrogen is going to end up on this right here, which is our hydronium ion. And then notice that hydroxide is kind of messy there, is actually left over. So here is my acid that water has made, and here is the base that water has made. So water by itself can make an acid and it can make a base. So does this worry you? Does this concern you? There is acid in that cup of water you're just about ready to drink? And the answer is, well, yes. Well, there's also base in your water too. Are you upset about that? And probably the answer is, well, probably not. Why are we not concerned about that acid and that base in your cup of water? And it's because it is such a small quantity that you never know it's there. Okay, it is, but it's not enough to think, oh my goodness, what am I doing to my body by drinking this stuff? Okay, so don't panic, don't worry, we're all set. So let's take a look at some math over here. And so here we have something called the ion product constant. Oh my goodness, there's a K all over again, like we did in that equilibrium chapter. And that K for W is called the dissociation constant for water. And notice, we are very specific. At 25 degrees, we have an ion dissociation constant for water. Why are we so specific about that temperature? Do you remember in chapter 14 when we talked about Le Chatelier? And we had to know if it was endo or exo, and if temperature went up, what happened to that K value? Oh, did it change when temperature changed? The answer is yes. So we do have to be very concerned with water, I'm sorry, with the temperature, so that we are always working with the right constant with the right temperature. So We're going to kind of revisit that thought shortly, but let's just kind of keep going on with this thought. So at 25 degrees, we know that this water molecule and this water molecule can collide with sufficient energy with the correct orientation, that once every so often it will break apart to make the hydronium ion and the hydroxide ion. You can also write this with just one water and making the hydrogen proton and the hydroxide. So we're just saying this one hydrogen is going to fall off of this water molecule. They're really saying the same thing. So that they're going to find out that that doesn't change a whole lot. So at 25 degrees, we can actually measure this Kw value. Now let's think for a minute. What kind of number is that? It's a -14. It's really, really small. So does it favor the products or the reactants? I sure hope you know it favors the reactants. This is such a small number, that P is so small and R is so big, that I'm not too worried about how much acid's being made, because that's such a small number. So what is it equal to? Well, products of reactants, I just said that. And when we talked about it in the past, we said if we were going to discuss what goes into a constant, it's either a gas, when you can have concentrations of gases or pressures of gases, or it could be aqueous solutions. So let's take a look at this equation here and see what we're going to put into the expression. Now, I hope you all realize that water is a liquid, and water is a liquid. So why is that important? Does water go into my dissociation expression? The answer is no. If I have any kind of an ion, the only way these ions exist, only way, is in an aqueous solution. So will these terms go into my K term? And the answer is yes. So when I do the Kw, which at 25 degrees, the constant is 1 times 10 to the -14th, we just said it's a really small number. What does that expression equal? Well, if I'm going to use that first equation, it's equal to the hydronium concentration times the hydroxide concentration. Notice that water is not in this term. Why not? Because they're liquids. I also have another equal sign. Why? Because what if I use the shorthand version? It's the same thing. My products is my H plus, my hydroxide is still there, and those are your concentrations, and I don't put the water in the denominator. Okay, so if this is a neutral solution, that means H plus is equal to OH minus. Okay, so if I were to use, let's say, this equation right here, and these two terms are equal, can I substitute those two terms? Sure can. That means if hydroxide is equal to the hydronium, and so these two terms are multiplied by each other, so I square them. Whoops, wrong term, sorry. Let's bring back another one. Here we go, this is the one I wanted. We're getting to that one later. Sorry about that. Okay, try this again. So I substituted here. Okay, so I square those two terms, and this is equal to 1 times 10 to the -14th. So that's this value up here. What am I going to do to solve for the hydronium? Hopefully you know I'm going to take the square root of both sides. What's the square root of 1 times 10 to the -14th? It is 1 times 10 to the -7th. So my H3O positive is this molarity, as is my hydroxide. They're equal. I didn't put the hydroxide in there, sorry about that. But they are equal. So hydroxide is equal to hydronium, which is 1 times 10 to the -7th molarity. How small is that really? Okay, here it is. So that's a really small number. Let's see here. This is tenths, hundredths, thousandths, 10,000s, 100,000s, millions. This is 1 in every 10 million particles, if you will, is going to be an acid. That's not much. I'm not worried about it, so phew. Okay, thank goodness. Let's look at problem number 13. It says at 60 degrees. Oh, wait a minute, what do you notice? This is at 25. This is at 60. I changed the temperature. The value of Kw has changed. Notice it's 1 times 10 to the -13th. It's different from this value. It says using Le Chatelier's principle, he doesn't go away, folks, predict whether the reaction below is exothermic or endothermic, okay? So let's think here. What has happened? Well, we know that at 60 degrees, K is larger. Sorry about that. Go away. K is larger than K at 25. 10 to the negative 13th is a bigger number than 10 to the negative 14th. So if K is larger, what does that mean? Think about it. Close your eyes if you have to. If K is larger, what does that mean about products and reactants? Which is now bigger? I sure hope you said the products are bigger when temperature went up. So, how did it shift? Hopefully you got it shifted right. So if it shifted to the right, that means it must be endothermic. Heat must be here. Let's make sure we understand that. So if this is where heat is, I'll put a little H here for heat. So if temperature goes up, it shifts to the right, making more products. If I make more products than I had before, the K is going to get bigger than what it was. So that does make sense to me. I hope it makes sense to you. All right, so what's next now? We're supposed to find what the H plus and the OH is in a neutral solution. Let me scroll this up again. All right, so what does it mean to be neutral? Well, in a neutral solution, hopefully you've heard of neutral and acid and bases before. If you think about it, neutral means that your acid equals your base. So once again, we can substitute in that same Kw expression. We can substitute, see how these are aqueous. So instead of having H3O plus times OH minus, then they're equal. So H3O squared is 1.3. Or excuse me, 1.0, if you will, times 10 to the negative 13th. So how am I going to solve for this? I'm going to take the square root, and there you go. Notice, isn't this number bigger than up here, 1 times 10 to the negative 7? Yes, it really is. It is larger than 1 times 10 to the negative 7. So we are correct. Products did increase. It did shift right. So again, I'm proving that it must be endothermic. All right, let's go to the next page. All right, so here are some terminology, here's some relationships that we really have to know. So in a neutral solution at 25 degrees, of course, again, that temperature is important. We know that the H plus and the OH minuses are equal, they're neutral, and they're equal to 1 times 10 to the negative 7. An acid solution, I hope this makes sense to you, that you have more acid than base in your solution. And a basic solution, I hope this makes sense to you, that base is going to be greater than your acid. And do you notice something over here? That's that same triangle we've used before. Remember moles on top of the mountain? Well, this time we have Kw on top of the mountain. And again, we're going to multiply these two numbers to get this. So how does this work? If you would like to solve for H3O plus, that's equal to Kw divided by hydroxide. If I want to solve for hydroxide, that's equal to Kw divided by H3O plus. So if I know the concentration of one of these two numbers at 25 degrees, of course, I can solve for the other one using this relationship. So in an acidic solution, if H3O positive is equal to 1 times 10 to the negative third, solve for hydroxide. So what am I going to do? Well, let's check this out. I do know that Kw is equal to H3O times OH minus. I'm so sorry. That, here we go, 1 times 10 to the negative 14th, and I substituted 1 times 10 to the negative third for the hydronium concentration. What are you going to do to solve for hydroxide? Yeah, you're going to divide by 1/1000th, and I hope you get this number. And of course, I'm always asking you, aren't I, does this make sense? And my answer is yes, it should. Because this number, 10 to the negative third molar, is bigger than 10 to the negative 11th molar. And we said an acid solution has greater acid than base, and so this does make sense. Hey guys, why don't you pause this? Solve for the hydronium ion in part B and see if it makes sense to you. So why don't you go ahead and pause this. Okie dokies, I'm back. So let me kind of throw this stuff up on the screen. And it does make sense. Why? Because 10 to the negative 2 is bigger than 10 to the negative 9. So the base is bigger than the acid, and it said it was basic. Let's see what the next one is. All right, so let's go ahead and look at problem number 14. This is done the same way as before. So set up your triangle, and we can do the first one together if you want. So what would you do to solve for the hydronium concentration? You would take 1 EE negative 14 in your calculator divided by 1 EE negative 5 and see what you get. When you do this, I sure hope you get 1 times 10 to the negative 9th. And now we have to determine whether the solution is acidic or basic. Well, which one's bigger? Is 10 to the negative 5th bigger or smaller than 10 to the negative 9th? I hope you got it's bigger. So the base is bigger than the acid, so it's basic. Let's try the next one. 1 times 10 to the negative 7. Go ahead and actually calculate that one out. I hope you got this. So now we have your base is equal to 1 times 10 to the negative 7th, and your acid is equal to 1 times 10 to the negative 7th. So what does that tell me? It tells me that the solutions are equal, so it's neither acidic or basic, so it must be neutral. Okay, let's do one more together and see how you do. So go ahead and see what you get when you plug this in. All right, so did you get 1 times 10 to the negative 14th divided by 10 is 1 times 10 to the negative 15th? I hope you did, because that's what I got. And so what's happening here? The H3O positive is actually bigger than the base, and so this whole solution is acidic. Go ahead and pause this and come up with the rest of these and see how you do. These are my answers. I hope that's what you got. And if you have any questions or if I make a mistake, tell me tomorrow or jot it down. But so here we have the values. I sure hope you came up with the ideas that 10 to the negative 5th is bigger than 10 to the negative 10th, so it must be acidic. Remember, this is your acid, and it's bigger than your base, so it's acidic. Over here, hopefully you found that 10 to the negative, whoa, that's not 16th. That's a silly mistake on my part. It's negative 6, isn't it? That's a typo. So it's 6.7 times 10 to the negative 6 is bigger than 10 to the negative 9th. So my base, the hydroxide, is a greater concentration than my acid. Over here, 10 to the negative 5th is bigger than 10 to the negative 10th. So my acid, my H3O plus, is in greater concentration than my hydroxide. And finally, over here, 10 to the negative 5th is greater than 10 to the negative 10th again. And so my base is actually in a bigger concentration. So I hope you got all that. And that's a lot of kind of cumbersome math, if you will. And the question is there an easier way to tell if it's an acid solution or a base solution than going through all this? I bet you already know the answer to that. And the answer is, well, yes. Let's turn the page and see what that is. And the solution, if you will, to our situation here is the pH scale. And let me kind of give you a little background on the pH scale. A guy named Soren Peter Sorensen. What a name. His parents must have thought that was a pretty funny joke. So Soren Peter Sorensen is a Swedish guy. Yeah, go ahead and say that. Yeah. And he went to college as a chemist. And when he got out of college, this has been a long time ago, mind you, probably, early 1900s. I think it was actually the late 1800s, if I remember that. And he was hired on by a brewery in Sweden. And his job was quality control. If you have a bad batch of beer, it is too acidic. And so his job was to determine which batches of beer were too acidic. Now, some folks out there, I know none of you, would say that would be the ideal job because all I have to do is taste it and know if it's nasty, it's too acidic, and after five taste tests, you have no idea what's going on. So there had to be a more of a scientific chemistry way of figuring this out. And so Soren Peter Sorensen, back in the late 1800s, came up with his own way to figure out the acidity of these batches of beers. So what he did, he came up with a pH scale. And what does P and the pH stand for? Do you even know this answer? It stands for power. Like power. No, not that power. In math class, what's another word for power? Is it exponent? Yes. So you're talking about the exponent. And what folks did back, even I did this back in the 1970s before calculators, is if you were working with really small numbers, you would take the log of those really small numbers, manipulate them, and turn them back into really small numbers if you want to add, subtract, multiply, or divide with them. And Soren Peter Sorensen did the exact same thing. He converted these itty bitty numbers into a log so that they turn out to be a little bit more normal looking. So why is it a negative log? Because if you try, just go ahead and put this number 1 times 10 to the negative 3 in your calculator. What do you get? Try it. Have you done it yet? You get a negative 3. Now, if you were Soren Peter Sorensen and you're making up your very own scale, do you like negatives? Well, you know what? He didn't either. So if you get rid of the negative in front of that negative log, you give a positive number. So now you get a positive 3. So the pH is a positive 3 because he doesn't like negatives. All right, so if this is your hydrogen ion concentration, what's the power? What's the exponent of 1 times 10 to the negative 7? What's the log of that? Take the negative of that, and that's your pH. Finally, do the same thing with the third one. What is the negative log? What is the negative power? What's the negative exponent of 1 times 10 to the negative 10th? It is 10. So that's what the pH scale is all about. Aren't these numbers a whole lot easier to work with than those 1.5 times 10 to the negative 15 or whatever we were dealing with? Yes, we don't have those decimal numbers now. We have real numbers. Now, did you notice something? Why did I put so many zeros at the end? I bet your calculator just gave you 3 and 7 and 10. Did they give you 3.00? No. So what does this mean? You are smarter than your calculator. We're looking at sig figs. All right, so right down here it says the number of decimal places in the log is equal to the number of figs of the original number. So here, look at that number out in front, 1.0, there's 2 sig figs. So how do I show 2 sig figs in a log? You take the numbers after the decimal. This number 3 is the exponent. The 0 implies this number here, let's say the coefficient. So if I have 1.00, that means there's 3 sig figs. So go back up here again. Ruh-roh, I left out some zeros. Oh, I left out a 0 here. I'm sorry. This has the right number of sig figs. This has the right number of sig figs. My bottom one, ruh-roh, Mrs. Vanderlei, what are you doing? Needs another 0 here. Why? Because how many sig figs are in this number? 3. So I need 3 decimal numbers over here. Okay. So let's check this out. Well, hey, before we go to the bottom here, what do you notice? Is this an acid, base, or neutral? 10 to the negative 3. Well, if you were to look at hydroxide, that'd be 10 to the negative 11th. Well, which is bigger? Your acid is bigger. So what does that mean? It is acidic. Okay, I said acid, by the way. Over here, what do you remember when the hydrogen ion is 10 to the negative 7? This is a special number. What's hydroxide? 10 to the negative 7. So what would that be? It is neutral. Does a pH of 7 ring a bell? Did you already know that was neutral? I hope so. And what about this? 10 to the negative 10th for hydrogen ion. That means your hydroxide is 10 to the negative 4th. So which is bigger, hydroxide or hydrogen? It's the hydroxide is a base. So look, acids have numbers smaller than 7, neutral has pH equal to 7, and bases have pHs greater than 7. Hopefully that seems familiar to you. So here it is. And here is your, like a number line. Anything below 7 is an acid, anything above 7 is a base. Neutral is equal to 7. All right, so let's check out problem number, I guess 15. So calculate the pH of each solution to indicate whether the solution is acidic or basic or neutral. So here is this is the same thing as an H. So that is the H plus. So H3O is H plus. So when I talk about pH, I'm talking about either one of these things. So pH is equal to the negative log of 1.8 times 10 to the negative 4. Will you plug that number in your calculator, hit log 1.8 EE negative 4? What do you get? Take the negative from that. You don't like negative numbers, neither did Soren Peter Sorensen. He put it as, here we go, 3.74. Notice 2 sig figs here, 2 numbers after my decimal. And now, is this an acid, base, or neutral? Well, this number is less than 7, so it's about right here. What do you think it is? It's an acid. Now let's take a look at the next one. Oh no, what's going on here? I gave you the hydroxide concentration. That's not pH. What do you think you have to solve for next? Go back to here. Oh no, I have to solve for H3O plus again, don't I? Go ahead and do that. Okay. So if you did it all right, hopefully you got, here is your H3O plus, and now you can take your negative log. Go for it. And now take away your negative, and that's what you get. We have one more page to do. I'll try to make it quick. I see I've already gone 25 minutes, so let's see what happens. Okay, problem number 16 says calculate the hydronium or the H plus concentration for a solution if I give you the pH. Well, what is the definition of a pH? It is a power. It is an exponent. It's the negative power. It's the negative exponent, base 10. So do you see what I did? pH, power, exponent. I made base 10, and I put this 4.8 as its exponent. I put the negative in front of it. If you get a positive number, very, very few times do you ever have a large number with this. So if you get like a 10 or a 20 or a 30 as your answer, you forgot your negative. So I just went, do you see where your log button is on your calculator? Do you see where if you go second log, it's at yellow 10x or maybe a blue 10x? That's what I just hit. So I just hit the second log button, and then I just typed in negative 4.8, hit the equal button, and voila. Now how many sig figs do I need? Look how many digits are after the decimal. I got 2, so this is 2 sig figs here. So I got 1.6 times 10 to the negative 5th. What's M? Oh, molarity. Isn't that what your brackets are? So will you do letter B for me and see what you get? Pause this. All right, hopefully you got it. Here's my work. Notice again, power of hydrogen, exponent, negative exponent, 10 to the negative 8.37. I got 4.3 times 10 to the negative 9th. Again, 2 sig figs, 2 sig figs. There you go. Now, folks, pH isn't the only P scale. We have POH. POH is a negative log of the hydroxide ion. Wow. Yeah. Love it. This is going to make math so much easier. Yeah. All right. Let's be like Soren Peter Sorensen. Yeah. All right. And what do you notice? There's a relationship here. Could that be pretty handy? Yeah. Do me a favor before we go on, and let's kind of go back to this page over here. Turn the page. Okay. Let's look at this again. Here is the pH I got from solving for the hydrogen ion concentration. But what could you solve for next? Find the POH. Hit your log button and hit this number right here. So what's the negative log of 1.8 times 10 to the negative 2? Did you get this number here? That's what I got when I hit that in my calculator. Now, what do you notice when I look at my pH and my POH? What do you think these two numbers add up to? That's right, 14. Do you think that's a coincidence? Have you seen that number 14 anyplace else? Oops, I guess it's over here. There it is. Oh, I do have an exponent. That's a 14. So in a sense, pKw, the power of the constant of water, is 14. It's not a coincidence. It does make math easier. So let's see where we are next. So it says problem number 17. Hang on. Okay, it says calculate pH and POH for each of the following solutions at 25 degrees. What if it weren't at 25 degrees? They wouldn't add up to 14 now, would they? So let's go ahead. What is the POH of hydroxide? This is really easy. Go ahead and plug it in your calculator. Hopefully you got that number. So you don't need to really calculate much more. 3 plus what equals 14? Hello, what do you get? I got 11 too. So is this an acid, base, or neutral? I hope you got as a base because pH, always look at your pH, is greater than 7. So let's write that down. So this is a base. Why? Because you're always looking at pH to determine this. Okie dokes, what about the next one? Well, wow, this is a 1. What's the pH of a solution of 1? Do your calculator, see what you get. Hopefully you got this. 0, that's right. So 10 to the 0 equals 1. That makes sense. So it's POH. Well, that was not too tough, was it? It adds up to 14, so POH is 14. So is this going to be an acid, base, or neutral? Well, look at your, oops, I didn't mean to cross it out. Look at your pH. It's less than 7. Always look at your pH. It's less than 7. It's an acid. So why don't you go ahead and do problem number 18. Pause this and see how you do. So it says the pH of a sample of human blood was measured at 7.41. Calculate everything basically, okay? Again, it's at 25 degrees. First of all, hang on a second. What's your blood? Is it acid, base, or neutral? Yes, your blood is basic. Not very basic, but slightly basic, okay? Keep that in mind for actually our next chapter. So here's my pH. P stands for power, stands for exponent, so I made it into a negative exponent, and here's my value. Now, I didn't do the hydroxide next. I found POH next, because what do these two numbers add up to? Yep, 14. So then I used power, hello, exponent, 10 to the negative 6.59 equals 2.6 times 10 to the negative 7th. And which one's a bigger number? Isn't this number bigger than this number? Yes, so my hydroxide is bigger concentration than my acid. That's right. Finally, last but not least, we have another common P scale. And we can take the pKa, we can take the pKb, we can take the pKw, we can take the pK, anything we want. And it's a negative log of whatever that constant is. So go ahead and find pKa. Here, pause it and see what you get. That's what you should get. That's it. Hopefully you enjoyed this. It was 32 minutes, a little bit longer than most of them. I apologize, but there's a lot to cover here. Talk to you later. Auf Wiedersehen. Yeah.